Okay, so now I want to start looking at, you know, more specific behavior of these polar roses. And so our first example is 6 sine of 3 theta. And so what I'm going to do is actually I'm going to switch over to Desmos. And in Desmos, I have 6 sine of 3 theta. And I made a slider for theta. Let theta be between 0 and a. And let's let our theta go up to 360 degrees. So right now I have switched into my degree mode. Okay. Now, so as I let A start going different values, I'm getting this nice, very, very symmetrical 3-petaled rose. And as A clicks through here, as it going through, these are the different values. So like this is A is equal to 136 degrees. And then we're going through, and we get back here, and that's 180 degrees. Notice that A is still continuing, right? It's going to go up to 360 degrees. But because this is an odd value, I'm only seeing the odd number. I'm only seeing 3 distinct petals. And in fact, once I get to 180 degrees, which is right there, I have the complete graph. So even though there are 6 petals total, because 3 times 2 is 6, only 3 of them are distinct. Now, why are we starting like right at the origin, right? Why do we start at the origin for this function? They all start there. And maybe you change 3 theta to 4 theta. Does that still start there? Yeah, it does, right? Maybe you change it to 5 theta. Does it still start there? Yeah, it does. If you wanted a different starting point, then you're going to have to pick a different function. Cosine. Cosine starts out here, right to the right, as opposed to the center. And think about, why is that? Well, sine of 0 is 0, which is at the origin. Cosine of 0 is 1, which would be at its greatest amplitude. You could relate that back to just our normal sine and cosine graphs, right? If you have a sine wave, sorry, it's not going to be very straight because I'm writing it sideways again. But our sine wave starts at the origin, right? Starts at equilibrium, goes to the max, reaches equilibrium, goes to the min, and it's right. And so there's really just there's 4 characteristic places on this graph. We've got the equilibrium. We've got when does it reach its highest amplitude. We have the equilibrium again, and then when does it reach its lowest amplitude? And then we start over. But a cosine graph, remember, a cosine graph begins at the highest amplitude. So for a cosine, it's starting at the highest amplitude. It goes to the equilibrium. It goes to the lowest point. It goes to the equilibrium, and then back to the highest point. So again, it's just based on the definition of our sine and cosine functions. So it should be no surprise that when I have a sine function, it starts at the origin because the sine of 0 is 0. Now, as we go out to that endpoint, right there, perfect, 30 degrees, right? 30 degrees, it's at its highest amplitude. It's at its greatest length from the origin. And after 30, it begins to decrease and become back into the origin. And right at 60 degrees, it's there. So the first 30 degrees, we get out to the highest amplitude. The next 30 degrees, we're back in. So I'm wondering if we go 30 degrees more, we'll be at the end of our next petal. And we are. It should be like there it is, 90. 90, we're at the end of our next petal. But I hope you have a little bit of a problem with 90 because it's pointing at 270, right? 90 degrees is up here, right? 90 degrees is up there, yet the graph is at the 270 mark. And that's because think about what is 3 times 90. If you put that into the equation, you're evaluating a 270, and the sine of 270 is negative 1, and negative 1 times 6 is 6. So we're getting that negative value. And so then I'm noticing this pattern that 30 degrees, the next set of 30, oops, I passed it. The next set of 30 would have been 120, and we're back at the origin. And then 30 more degrees after 120 is, I passed it, is 150. And 150 actually is right where 150 should be, right? So remember, we were at 90 and we were down here. We're at 30 and we're up here. We're at 150 and we're over there. And again, why is it doing that? And then 180 right there. Well, it's doing that because our sine graph, if you think back to just our old sine graph, you start at 0, you reach the highest equilibrium, you go back, or highest amplitude, you go back to 0, which is the equilibrium, and then you go to the negative amplitude. So a negative amplitude is going to be associated with a negative radius here. And so if I think about it as this graph, 0, there's 30 degrees. Here comes 60 degrees. When I get to 90 degrees, there's my negative amplitude, which would be the end of that second pedal. And then 120 degrees, we're back at 0. 150 degrees, we're at the maximum amplitude. And then back to 180, we are at 0. And, every 30 degrees, we were able to find the different points. And that's not just the sine function. That could have been cosine as well. The difference is cosine is going to have a different starting point because cosine is going to start at its maximum value. So then here's 30 degrees. We're back at the origin. Here comes 60 degrees right there. And notice that even though it's pointing at 240, it's really 60 degrees with a negative radius. And then 90 degrees will be back in the origin. And then 120 degrees is the next increment of 30. 150 degrees is here. And then when we get to 180 degrees, we'll have seen the whole graph, right? We'll have seen the whole graph. But notice 180 degrees, that's over here with a negative radius. It puts us back at the start. And so again, the question is, why was 30 degrees such a key value? Well, because if you think about normally we graph things every pi over 2, right? Every pi over 2 has every pi over 2 has something that our graph has a feature of, like either it's a positive amplitude, or it's 0, or it's negative amplitude. Well, pi over 2, that's the same thing as 90 degrees. And so if I have like 6 sine of 3 theta, so instead of saying, well, every pi over 2 or every 90 degrees something's happening, that coefficient of 3 means, 90 over 3. Now every 30 degrees something is happening. And so when I go back to my graph and I'm asked to sketch this by hand, I know that every 30 degrees something important is happening. And so sometimes when we first start writing and drawing these, you could draw an R and a theta, and you can start going every 30 degrees and start listing a table of values. And even though we've already seen these, every 30 degrees, I think it's helpful to know what's happening. So if you have 0 degrees and you're putting 0 in for theta, right? And so then theta, so 0 times 3 is still 0. Sine of 0 is 0. So I know it starts out at 0. Then you go 30 degrees. So you put 30 degrees in there. 30 times 3 is 90. So sine of 90, it's the highest amplitude. So we get a radius of 6. 60 degrees, that's 3 times 60, so it's 180. Sine of 180 is back to 0. 90 degrees, so again, 90 degrees is sine 3 times 90 is 270. That's a negative 1, so we're at negative 6. And then you put in 120, you're back to 0. And really look at this pattern: 0, 6, 0, negative 6, 0, 6. 0, negative 6, 0, 6, 0, negative 6. Again, you're just getting the highs and the lows if you were to graph this, on the XY plane. So once you know why it's every 30 degrees, then we could even plot the points here. Now I'm going to ask you to do this each time, to put a star, doesn't have to be in yellow, put a star where this graph starts. And we want to kind of indicate these points. So I need to get to 6, 30 degrees. So 1, 2, 3, 4, 5, 6. So it's right there. And I might go back to just a normal color here, blue. So it's right there. So I have to get from the star to this point right here, which is 6, 30 degrees. Well, I can either go like this to get to that point, or I could go like this to get to that point. And obviously we have a Desmos in our graphing calculator. We can see the direction, but we should wonder why. Why is it that we're going to approach this star to that point in this direction? And the reason we're going in that direction is because that's counterclockwise. That's exactly how we graph, or that's how we analyze the unit circle. So I'm going to also ask you to put arrows to indicate the direction. We're going in that direction. And then we need to get back to the start. So even though it says 60 degrees, I know that the start is 0 again. So I don't have to label that because I'm going to come into that quite a few times. And now I need to get to negative 690. Well, negative 690 is down here. So 1, 2, 3, 4, 5, 6. Right? So negative 690 degrees. So now I'm going to kind of arch through here. Again, still showing the arrow of that direction. And then the next point is 120 degrees, but it's back to a radius of 0. So I'm back in the origin. So again, showing that arrow, right? Or moving in that counterclockwise direction. And then we need 150 degrees. And so you kind of anticipate it's going to be over here somewhere if you follow that curvature. So 1, 2, 3, 4, 5, 6. Oops, sorry, I didn't mean to erase. So 6, 150. Again, I'm labeling and kind of going out in this curvature here, showing those arrows, and then back to the start at 180 degrees. Now, again, just illustrating that we only needed 180 degrees, even though that's halfway around the unit circle. We have our distinct, right? We've got our 3 distinct petals. I don't have to go any overlap. Also, I don't have to label the origin each time because otherwise it's going to get kind of messy. One question that does come up in this class is like, well, how wide are your petals going to be each time? And the thing is, the more petals you have, the narrower they are. But in order to know what is that maximum width, you need a little bit of calculus. So for now, we're just going to not worry about it, just kind of draw a sketch. And, the other thing I like to highlight too is that going from any petal tip, so from this petal tip to this petal tip, you could also graph it in a smooth motion. Like I know I've got to get through the origin, so the curvature of this should be like one kind of fluid motion. And then the curvature from this point to that point should be another, fluid motion. And it's actually going to be the same arc that you just drew in green. And like our final one, again, just this nice fluid motion. If I were to have connected over to there. So, again, our goal, I spent a lot of time on this one problem, but our goal, remember, is to be able to look at that polar rose and say, okay, I know it's a polar rose because it's a sine or a cosine, has an amplitude and a frequency change. Now, what is happening each time? Your amplitude, that's going to affect how long your petals are, right? So your petal length in this case was 6. That had to do everything with the coefficient of A. And then how frequently do we go to that value? Take your frequency, and whether it's even or odd, take your frequency and divide 90 by that value. And so we'll look at some more examples. Again, part of this getting good at polar graphing is you're going to play around with a little bit, maybe on your calculator, on Desmos, and until you feel comfortable knowing what is the effect of each coefficient.